This video is for the evidence number 4. I'll talk about the change processes of materials. My name is Ernesto Gallegos, so let's begin. Those are the 4 types of materials we'll be talking about in this video. First one, metals. Second, alloys. Third, ceramics. And the last one, polymers. Let's begin with metals. And well, iron-based alloys, particularly the carbon and low alloy steels, are among the most widely used structural materials in industry. Structure change can be achieved easily in iron carbon alloys using straightforward thermal treatments that rely on the change in solubility for carbon and alloying elements that accompany iron's allotropic transformations. As expected, mechanical properties vary with the structure. Furnace cools, just as an example, just to mention something, a slow cooling rate. Materials exhibit low strength and high ductilities since they are fully annealed, while rapidly cooled materials, for example, water, oil, or air, quenched depending on the alloy content, exhibit higher strengths and lower ductilities. Volume change accompanying the austenite martensite transformation can lead to high residual stresses and substantial distortion, along with a risk of part cracking due to differential cooling in parts with large changes in cross sections. Hence, hardened parts are usually tempered to relieve the stresses and to stabilize the part dimensions. Structure change processes in non-ferrous, for example in aluminum alloys, are widely used in aerospace construction and are finding increased use in the automotive industry to reduce vehicle weight. These materials depend on change in solubility of alloying elements with temperature. However, in the absence of allotropic transformation in the base material, change in mechanical properties depend on solution treatment, followed by precipitation aging. The final structure and properties in these dispersion hardened materials depend on the times and temperatures used for the precipitation treatment. The upper, the upper temperature limit for the use of these alloys is determined by the propensity of the precipitates to coalesce and coercine. For example, superalloys used to build the hot section components of turbine engines rely on a structure comprising a nickel matrix with a fine dispersion of highly stable gamma prime precipitates that possess a good lattice match with the matrix. Such a microstructure retains its strength even at relatively high temperatures, hence the name superalloys. So now let's talk about ceramics. In this case, the principles of structure change in ceramics are similar to those for metallic materials. However, the thermal treatment practice is handicapped by the low thermal diffusivity inherent to ceramics. Also, slow heating and cooling rates are used to minimize risk of cracking by thermal stresses. This problem is aggravated by the higher thermal treatment temperatures necessary for structure change in ceramics. Structure change is nominally amorphous ceramic materials uses thermal and thermomechanical treatments comparable to those for metals and alloys. Glass ceramic oven tops, for example, are mechanically processed and thermally treated to create a final microstructure with a very low thermal coefficient of expansion. Exceptional thermal shock resistance is obtained through control of microstructure. Ceramics pose problems in structure change because of the directionality of their molecular bonding, high inherent hardness, slow achievement of equilibration, limited number of slip systems with resulting very low ductility, and the presence of hard and soft glide plants. Despite these limitations, thermally treatable taught ceramics such as partially stabilized zirconia have been developed and are finding increasing use as structural ceramics. It's time to talk about polymers. Nominally amorphous polymeric materials are normally processed by melt to solid transformations. However, extraordinary strength gains can be obtained in some polymers, just for example in the polyethylene, by controlled deformation in the processing of fibers. Precise strain rates, and thermal treatments are necessary. Structure change processing to obtain high strengths in common polymers is not widely used. Injection molded tabular polyethylene terephthalate performs as stretching below molded when the material is elastomeric. Processing conditions are selected and used to prevent any structure change between injection molding and heating for blow molding. Process temperature and time are adjusted to suppress spherulite formation and to promote partial crystallization. Final strengths obtained in the part, just for example in plastic beverage containers, are comparable to those of aluminum alloys. And yet, we still have research opportunities. The structure change in metallic alloys, ceramics, and polymers has a sound theoretical basis. The structure change processes in use are well established and understood. The ease with which structure change can be affected in metallic alloys has led to the widely used industrial practice of fabricating metallic parts in their soft condition, followed by structure change processing either as a final or penultimate treatment to obtain the design properties. A major deficiency in structure change processing for discrete parts is its frequent dependence on batch processing for thermal treatment, since undesirable storage queues are typically required. Two recent developments offer a means of overcoming this problem. Solid state high frequency power sources in continuous mode, pulse, and solid state lasers. Both developments permit rapid inline structure change processing, which eliminates the need for batch processing, and hence implant storage is minimized. Structural changes can be induced in almost all engineering materials to alter their properties. This is usually achieved through thermal treatments involving heating and cooling under controlled conditions. The treatment temperatures and processing conditions vary according to the nature and composition of the material. Combinations of mechanical and thermal treatments are sometimes used. In example, in thermomechanical treatments to produce properties that cannot be obtained in any other way. In some cases, different properties are desired in the bulk than in the surface of a part. In these instances, specialized thermal treatments involving surface diffusions or surface heating are used. And just to finish, this is going to be the end of this presentation. This is my own conclusion about the importance of the materials transformation. So, I consider it very, very important as millions of people do. And it is because, thanks to the ability and skills that humanity has reached, discovered, and learned throughout all of its history, we are in the industrial point we are today. Because we had the opportunity to build up the cities and all of its components. Also, the things that are making our life easier. I mean, the things that are making our lives easier. Just to mention an example, let's say your car. Nowadays, you cannot imagine your life without your car, your cell phone, your house, etc., etc., and the list could go on and on and on forever and ever. The real question is, does anyone believe that man was born knowing already how to create, to build or manufacture all of the materials that are present in our daily lives? Of course not. Humanity had to learn since the very beginning how to create every single piece that is part of the foundations of the nowadays society. Thanks to their intelligence and why not? Also, thanks to their imagination, they discovered and invented several ways to change the shape and properties of the materials surrounding them because they wanted to get better things to survive and improve the conditions where they were living in. And thanks to their perseverance, they achieved their goal, their purpose, and now we're enjoying those results. Fortunately, thanks to them, of course, we know all of those techniques: forming, hydroforming, forging, extrusion, punching, stamping, and a lot of different ways to even change the inner properties of these materials to make them useful to the purpose we have in mind. So we can continue with the exponential growth we're having as human race. Without the abilities we have as human race, I believe we will still be living in the Middle Age, dreaming with the Industrial Revolution that will never come. So that's my conclusion. And thank you for listening to me. So this is the end of my presentation. Thank you again and have a wonderful day.